This video is going to cover the virtual work method for beams. In this example, we want to find the maximum deflection of this beam. Now this is a little bit tricky because we don't exactly know where the maximum deflection of this beam is going to take place. But what we do know about it is that for the deflected shape, the point of maximum deflection has a tangent line whose slope is equal to 0 degrees. That's going to be our key piece of information for finding the maximum deflection. So the first thing that we need to do is analyze this beam under the given loading and find our reaction forces. We have AY, we have AX, and we have BY. Now if you sum the forces in the x direction and set it equal to 0, you're going to get that AX equals 0. If you sum the moments about A and set it equal to 0, we're going to have BY times 6 meters going in our positive direction. And then we're going to have 15 kilonewtons per meter going in the negative direction. So negative 1/2 the base of 6 meters, the height of 15 kilonewtons per meter, times the distance from his centroid, which is about there, so 2/3 of the base. That's going to give us BY equal to 30 kilonewtons. And this is going up. Then, if we sum the forces in the y direction and set it equal to 0, we have AY going up, we have BY going up, and we have minus 1/2 times the base of 6 meters times the height of 15 kilonewtons per meter. So AY is going to equal 15 kilonewtons, also going up. So we need to make a cut so that we can analyze our moment equation in terms of x. Now our loading situation doesn't change anywhere in here from A to B. It's going to be a continuous, linearly increasing load that goes across the whole beam. So we can make a cut. It doesn't matter wherever. So we're going to make a cut right there. So now we need to analyze our cut. So we have a small section of beam where we have AY on the end, which we said was 15 kilonewtons. Our cut is going to be a distance of x. We have our load situation of 15 kilonewtons per meter across our 6 meters. Now this is the tricky part, is how to determine what the value is that we're going to stick up here. So we're going to do similar triangles. If I want to find what the value is right here, then let's do a similar triangle. We have across 6 meters, we have a height of 15. So across x meters, we're going to have a height of y. So 15 over 6 is equal to the y height over x. So our y height is going to equal 15 over 6 times x. So we're going to put that right here. This is 15 over 6 times x. Then since we made a cut, we have internal shears, internal normals, and internal moments. And the moment is what we care about. So we're going to sum the moments about the cut and set it equal to 0, taking our normal counterclockwise to be positive. And we're going to write out our equation for what the internal moment is in terms of x. So we're going to start left to right. We have our 15 kilonewton force. He's going to be going this way around. that's going to be negative. So minus 15 kilonewtons times his distance of x. Then we have our 15 over 6 times x, linearly increasing load over here. He's going to cause a rotation this way, which is positive. So we have plus 15 over 6 times x, that's the height. And we technically need 1/2 times the base as well. Then the distance from his centroid over to the point about the moment, that's going to be 1/3 of that base of x. Then don't forget we also have our moment. So rearrange to solve for m, and we're going to get that m is equal to 15x minus 5 over 12 times x cubed. Now remember, he's the same throughout the entire thing. So we have our moment equation in terms of x. Now, the next step is to unload the beam. So here we have our beam unloaded. We just simply have a pin and a roller on our 6-meter beam. We have a new AY and a new BY, technically a new AX, and we need to apply, because we want to find slope so that we can set slope to 0 to find that distance, we need to apply a rotation. This rotation has a unit of 1. It's just a point moment of size 1. Now again, we don't know the distance to this guy, so we're going to call that D. So now we need to analyze this beam. So to start with, let's find our new reaction forces AY and BY. So we can do this by summing the moments about A, just like we did before. So we have minus 1 for that point moment that we have, and then we have BY, so plus BY times 6. So BY is equal to 1/6. If we sum the forces in the y direction and set it equal to 0, we just have AY and BY. So AY is the opposite, so he is negative 1/6. So that's our beam. Now, we want to make the same cuts as we did before. However, our loading system has changed. So what we need to keep constant is the direction we're taking our x. So we're going to call this x1. So we have a cut here before the load, and then we're going to make another cut after the load. And x2 has to be in the same way. The reason being is because that's where our moment equation came from for the given loading system, right? Because in here, it doesn't matter that we're taking a cut here and that we're taking a cut here. The moment equation did not change for the given system. So technically, we're not violating any rules there. So now that we made our cuts, let's analyze our sections. So for section 1, we're going to go from 0 to x, and his maximum distance is D. D is the distance where that point moment is applied. So we're going to go from 0 to x all the way to D. So let's draw our little fragment of a diagram here. Got our little beam. Remember that we have AY, and AY was going down 1/6. This distance is x1, and we really don't have any loading at all. Don't even have that point moment. So we have shears, normals, and our internal baby moment M1. So if we sum the moments about our cut and set it equal to 0. All we have is little baby moment m1, and we've also got 1 over 6 times x1. That was our AY. So little m1 is equal to negative 1/6 x1. Okay, that's all nice and good. Next, we're going to analyze it for section 2. In section 2, x is going to go from D. We got to pick up where x1 was. So we're going to go from D all the way to the end. So we're going to go from D to x to 6. So we're going to draw our new little beam section. Now remember that for x2, we're actually going all the way from the left side all the way over. So we are still going to have AY. AY was 1/6 going down. But our x2 distance goes all the way past where that point moment was applied. And remember, that distance was D. So again, we're going to analyze it for our internal shear, normal, and little moment M2. So we're going to sum the moments about the cut, set it equal to 0, taking counterclockwise to be positive. Again, we're going to go from left to right. We've got our 1/6 times x2 for our AY. We have -1 for that point moment, and then we have plus M2. So M2 is equal to 1 minus 1 over 6 x2. Really not a bad equation. So now what we want to do is use our equation, where slope is equal to the integral of the length of our cut of big M times little m over EI dx. That's our equation. And remember, we can set him equal to 0 because we're finding the distance. So we're going to use our length to get from 0 to D, and then D to 6. So 0 is equal to the integral. For section 1, we go from 0 to D of big M being 15x minus 5 over 12 times x cubed. So we have 15x minus 5 over 12x cubed times little m1, which we said was minus 1/6 x1, all over EI dx1. Okay, then we need to add in the integral for section 2, who went from D to 6 meters, of again big M 15x minus 5 over 12x cubed times little m, which was 1 minus 1 over 6 x2. All that over EI dx2. So when we're going to solve for this, we have 0 is equal to, when we take our integral, we're going to get negative 15 over 18 times x cubed plus 5 over 360 x to the 5th. That's the first integral, and remember he's going to be going from 0 to D, plus our second one, which is 15 over 2 x squared minus 15 over 18 x cubed minus 5 over 48 x to the fourth plus 5 over 360 x to the fifth. All of that evaluated over D to 6 meters. So when you solve for this, you're going to get a fourth degree polynomial. So 0 is equal to negative 5 over 48 d to the fourth plus 7.5 d squared minus 63. And when you solve this fourth degree polynomial, you're going to get 4 roots for d. You're going to get negative 7.89, negative 3.12, positive 3.12, and positive 7.89. Now the question is, which one of these roots is the correct one for D? Well, which ones make sense? Honestly, this doesn't make sense and this doesn't make sense. How can you have a negative value for the distance to your beam? If your beam only goes from 0 to 6, how can you have a negative 7.89? That's not even on the beam. How honestly can you have 7.89? That's off your beam. If your beam only goes from 0 to 6, then the only one who makes sense is 3.12. So great, we found D. So now that we have our distance to our deflection, now we're going to analyze our beam all over again, but now we want to find deflection. So on our beam, we're going to come back and add a point downward force of 1 at our distance of D, which was 3.12. So of course then the other direction is 2.88 because our grand total beam is 6 meters. And we're going to do the same thing. We're going to analyze it all over again. Now again, we still have to make 2 cuts because we have 2 different loading situations. One before the load, one after the load. So same 2 cuts that we just did. We're going to analyze it. It's going to be slightly different. So we still have AY and BY. Let's start off by solving for those. So if we sum the moments about A and set it equal to 0, we're going to get, we have our minus 1 load there, times his distance of 3.12, plus we have BY times 6. So BY is equal to 0.52. And if we sum the forces in the y direction and set it equal to 0, we have AY plus BY minus 1. So AY is equal to 0.48. Cool. So now, knowing that information, let's make our cuts. So section 1 goes from 0 to x to D, which was 3.12. Right, so x1, and then our x2 is going to go out there. So let's start by drawing our beam. So on our beam, we have our AY reaction, which is 0.48. And we don't actually get far enough to include our load. So we have shears down, normals over, and little baby m1. Of course, this distance is x1. So if we sum the moments about the cut, set it equal to 0, we're going to find that we have negative 0.48 times x1 plus m1. So m1 is equal to 0.48 x1. That is much simpler. Then let's analyze section 2. So section 2 goes from 3.12 to x to 6. So we're going to redraw our little beam. Our little beam still has AY. AY we said was positive 0.48. This time we have a point load down of 1. And don't forget that his distance was 3.12. We have x2 across the bottom, and we have internal shears, normals, and moments, little moment 2 at the cut. So again, we're going to sum the moments at the cut, set it equal to 0, counterclockwise to be positive. So again, left to right, we have negative 0.48 times x2, plus we have 1 times his distance. His distance is x2 minus 3.12. Then don't forget we also have little m2. So m2, believe it or not, is going to simplify down to 3.12 minus 0.52 x2. If you're wondering where the 0.52 x2 came from, you have 1 x2 and minus 0.48 x2. That's where that came from. So we have our m1 and our m2 equation. So now we want to find deflection. That's going to be the integral of section 1, who went from 0 to 3.12, of big M, he hasn't changed. So 15x minus 5 over 12 x cubed times little m1, 0.48x, all that over EI times dx1, plus the integral for section 2, who goes from 3.12 to 6, of big M, still hasn't changed, 15x minus 5 over 12 x cubed times m2, 3.12 minus 0.52x, all this over EI times dx2. And when you solve for this lovely integral, you're going to get the deflection is equal to 126.8 kilonewtons meters cubed over EI. And you'll find, this is going down, you'll find that this is the exact same number as what's in your solids appendix C.